Welcome everyone, it's Mr. Who back with some more trig. Now, since we talked about our trig functions and applying them to triangles, now we're going to talk about how they appear in the regular plane. We're going to call these, in this little unit, okay, sinusoidal, okay, functions. Okay, we call them sinusoidal, obviously, because it's based off of sine. So what you're looking at right now, the picture on the Desmos graph, is, of course, the graph for the basic function f of x, or maybe I should use theta, but I'll use x, okay, but that x really means theta, okay, sine of theta, okay. There is no easy way for me to type this, obviously, so we'll talk about that later. Of course, you can't really talk about sine without talking about its brother, cosine, so that is also what we're going to talk about today, but right now we're looking at sine. So let's just talk a little bit about these. So first of all, you'll notice that it's a nice wavy shape. Okay. I'm going to get started with our basics. Okay. So the basics are that these are periodic. That means the graph itself, the behavior as you take it out very long to the right or to the left, is that it loops. Okay. These graphs loop. So unlike your quadratic, your rational, your exponential functions, these functions don't really go towards infinity. They kind of hover around the same points, and they kind of repeat over and over in a pattern. Okay, and that's what we call a period. You will learn about that once you get to the features. The second thing about these graphs are that they are based on the y or x values in the unit circle. So remember, based on whether you're talking about the y, sine, or x, cosine, oops, not with a zero, okay, you are basically talking about the output that is in the circle. So if you need to go back and review a bit more about the circle, that is something you can do, but I'm going to show it really quick here. This is sine, remember. Remember, sine of 0 degrees is, well, 0, if you look at your notes from before. The sine of 90 degrees was 1, which is about here. Okay. Sine of 180 degrees was negative, or was 0 again, sorry. And then 270 was negative 1, and back to 360 for the 0. Okay. You will notice that I have it displayed in radians. So if you're not quite comfortable with radians yet, you may have to revisit those or start getting a feel for it. If you need a quick little reminder of how they translate, you simply have to take the radian and multiply by 180 over pi, okay, to get your degree measure. In this case, it would be 45 degrees. Okay. So each of these little ticks represents a 45-degree measurement. Alrighty. Now let's talk a little bit about some differences between sine and cosine. So let me get that ready here for you. Okay, so now I have both sine and cosine out here for you. It may be pretty hard to tell which one is which right now, but in the blue, we have the cosine graph. Okay. And in the red, we have the sine graph. Okay, so let's talk about those differences. There are almost no differences visually between the two types of graphs. The only real difference, which I'll type out for you, is that cosine starts at 1. Okay. And sine starts at 0. Okay. I might also go on to say that cosine starts at its peak, while sine starts in the middle, I want to say. Or what we like to call the midline. Okay, so you'll learn more about that once we get to that as well. So those are the main differences between cosine and sine on the graph. Okay, but in order to understand these a little better and be, at the level where we want you to be, we actually have to talk about some of these features I've been dropping here and there. Specifically, we're going to talk about 3 different features. That would be the midline, if I can find the right typing, okay, the amplitude, and the period. So please make a section in your notes for those as we talk about each of these using the sine graph. Using the sine graph, I will talk about it with that. So let's start with the midline first. You heard me say that word about how the sine was centered at the midline, or starts at the midline. So here's a definition for midline. You may want to write down in your notes. Okay, the midline is the line, okay, horizontal, I should say, horizontal line that the function is centered on. Horizontal line that the function is centered on. So if I'm looking at our sine graph, our lovely sine graph here, that's a basic one, remember? F of, this is theta, I'm actually going to use theta, sine theta, okay, for angle measure. Okay, and I'm talking about the very basic sine function. And remember I said sine starts at where the midline would be. The midline is a horizontal line, so my midline for the sine's basic function is the line y equals 0. Okay, so as you can see, kind of from the picture, it's kind of cutting straight through the pieces, like the little wave up and wave down, and it is definitely where this sine function starts. Okay, for cosine, it'd probably be in the same location, the base one, but it would not be where the function starts because you start at the top, the peak. All right, and that's pretty much all you need to know about the midline. The midline does manifest itself in the equation, okay, as this guy right here. Okay, if I were to add some constant to the outside of our sinusoidal function, whether it's sine or cosine, this would be our midline, okay, shift. Which, don't worry if you're not super hot on this equation I'm adding here. I will put a final version of like every feature you need to keep in mind for today. Okay, next up is amplitude. So amplitude is maybe something you heard if you took physics and you were studying some maybe sound or wave motion. But the amplitude is basically the height and depth of your function. Or of the, I guess, sinusoidal function. So let's take a think about this. If I'm talking about the height and depth, you may interpret that as perhaps right here. This is the highest high, and right here, which is the lowest low. Okay. And when we talk about amplitude, I am actually talking about this length right here. Okay. And not the whole length, just one piece of the length. So from here, the midline, to the top of our sine graph, our sine function, the amplitude would be 1, because that's how tall my hump is, my little hump. That's how short my other hump is, my dip. Okay. So when we see that, 1 and -1 are the highest and lowest values from the midline. Okay. That's our amplitude. So if the midline happens to shift, you need to account for that by thinking about where it is and then figuring out the amplitude from that. If you're thinking about the function f of theta equals sine, oops, I did 2 equals sine on accident, equals sine theta, okay. This amplitude would manifest right here as maybe like a constant a multiplying constant in front of our sine. In this case, it doesn't really appear because it's a 1, but if this is any other amplitude, like 2 or 3, it would be up here in the front. All right, the last feature I'm going to introduce you today is the period. So the period I mentioned before is basically how long it takes for your function to loop, okay, to loop, or start over. So if we're talking about our sine function here, there will be a part in which you can definitely see it restarts the pattern. This is the same as if you were looking at the unit circle. Okay, where is that measurement? Hopefully you know. Okay, maybe take a guess, but it should be at this point 2 pi. So from 0, which is our starting point, to 2 pi, okay, this 2 pi distance is our period. Okay, and that's how long it takes to loop. If you see over here, once it hits 2 pi, it shows the same hump as the starting hump, right? So after this point, this 2 pi point, you can expect to see the same little up and down swing that sine loves to do. Okay, and in the function anyway, which I will definitely give a whole version of the function in a sec, and we'll probably explore it next time, but for now, we'll just talk about it here. F of theta is sine theta as the basis, okay. But sometimes there is a constant b in there, and we use this b, okay, to describe our period, which is actually found by getting 2 pi divided by b. So if right now this b is 1, my period would be 2 pi. But if I change my b to any other number, let's say like pi over 2, okay, then that would change my period. Okay. Although typically you're not going to put a pi in there. Usually it's just constants. So that way we keep our pi. But yeah, that's our period for you. Okay. Basically it takes however long to loop is our period. Okay, so I'm going to leave this off with a general form of these types of functions. Basically, you are doing this in terms of theta. So don't think of this as really an x. Think of it more of an angle measure. That's why I'm using theta here. That's why we have it radians on our x-axis. And so if you're talking about sine, let's use sine here, since you're doing that the whole time. There are 3 main parts. The a in front of the sine, the b inside the sine's parentheses, and the c on the outside. Okay. And they all correspond to different features. This a is corresponding directly to your amplitude. A for amplitude. Very easy, right? Okay, and it's a direct correlation. Whatever this number is our amplitude. Okay. Although we don't care about negatives, so be careful on that. The second number, which is b, okay, is our period, or is used to help find our period with 2 pi over b. Okay. And finally, we have our c. This represents our midline. Okay. And typically the default is 0, but this also correlates directly with the number. So you don't have to do any extra math for that. Where this one is sign matters. Okay. And I got to go back and hit this up. Amplitude, never negative. All right. So those are all the 3 basic things we're looking at here. So let's take a look at some examples before I get too deep into this. Okay, so here we can see that I have an A, a B, and a C. Now I have sliders, okay, which I can display that later as kind of a fun little excursion. But basically, changing the value of A has a direct effect on the amplitude, the height, or the depth of our sine function. So let's change this, for example. Right now it's 1, the base form of the function. But let's say I want to raise it to 2. Okay, well, the graph obviously changed. Did you see that? And if you don't, you can go back and pause it and replay it. But now the height of the whole hump and the depth should go down to -2. But that's a direct correlation to our amplitude. Okay, and we'll never call it negative, so our amplitude is 2. So let me go ahead and mess around with this. If you want to mess around with it yourself, you can format it just like I have here in the notes with Desmos, and you can mess around with it yourself. Okay, but you can even make it lower if you want to go like 0.5. You can make it smaller. Okay, it's pretty much whatever you want it to do. Okay, whether you want the amplitude to be really high or really low. The next one is our B. Okay, that's the stuff on the inside, right? So watch what happens here. If I change B to be 2, okay, well now there happens to be a bit more waves happening at a bigger frequency. Okay, and you can see here that when I look at the graph, now instead of ending at 2 pi, which is over here previously, now I'm restarting the function's shape at regular pi. So that's tying into our little formula there for period. Right. So just like with the other one, if you want to mess around with this, you can make it as like wavy or as unwavy as you want. If you go higher and higher, your waves will get more frequent. But let's say you go lower and lower, well, your waves will get longer and longer, right? 0.25. Let's see that. Ooh, look at that. Really long stuff there. But of course, the default is 1, right? The default is 1. Finally, we have that last bit, the C, the pesky one. Okay. Although this one is not so pesky as you would probably believe. Right now it's at 0. Remember, this refers to the midline. So if I change it to something like 1, Well, now my whole graph has shifted up a whole point, right? So now instead of being at 0, it is now at 1. Oh, okay. But unlike the amplitude, this one can be negative, so if you shift it down -1, suddenly it's moved down there. But if you add 2, okay, then it goes up even more, 3, up even more. So this one doesn't actually change the shape, it just moves it around vertically. Okay, so let's put it back down to 0. And that's pretty much how these look in the plane. Okay, and of course, all of this applies to cosine too, which you can mess around with if you toggle this, and you can just try to change it around. Okay, which I'll go ahead and play these, so you can see kind of how they work, right? Whoa. Okay, I can pause it whenever I want. So right there, that's a very nice looking one. Okay, can I move this around? Oh, they all shifted up now. Okay, so really guys, if after these notes videos you kind of get a feel for the idea of it, but you just want to mess around with how these shapes form, please take a look at Desmos. We'll definitely talk about this with the practice in class. Okay, and take a look at some delta math problems too. Remember, this is introduction, so don't feel like you have to master this right away. Okay, we will definitely have time to talk about it, and more time, of course, after this week. All right, so the last thing I want to say is, based off these notes, here's what I tried to hit. I wanted to answer the questions, what are sinusoidal or periodic functions? What are those features that they commonly use? So the midline, amplitude, and period. And how do those features correspond to the written functions? So the ones I really want you to worry about are probably point number 2 and point number 3. If you know those, you'll definitely be able to breeze through the IP in no time flat. Okay, and make sure to bring questions to class. Okay, if you're watching this in class, make sure to write in your questions during the slide practice. I'll see you guys later. Mr. Who out.